Hello and welcome to College Physics 1, Lecture 16, Dynamics and Newton's Laws. In our most recent lecture, we looked at equilibrium and Newton's laws. Equilibrium being any situation where your object is either at rest or moving at a constant speed in a straight line, so that in either case the acceleration is zero, so there's no net force acting on your object. Here, we're going to take away that simplifying factor and say that there is going to be acceleration, and so now we're going to look at kind of the true problem involving dynamics. Newton's second law in component form is fairly straightforward at this point. We've already written it down in our past lecture. In the last lecture, though, we said that the sum of forces in the x and y direction were equal to zero because the object was in equilibrium. Well, here that's not necessarily the case. So we can't just say it's equal to zero anymore. We say that it's equal to ma. In other words, this is just F equals ma. So the formal and kind of full way to write Newton's second law is what you see on the screen here. The sum of forces in the x direction is equal to max, and the sum of forces in the y direction is equal to may. So, we're going to just solve a couple more problems in this lecture, this time looking at dynamics problems. So let's kind of make a new step-by-step guide on how to solve this type of problem before we go into solving two of them in this lecture. Overall, though, the process is still the same. You're going to draw a free body diagram and you're going to write out Newton's second law. In fact, that's the first two steps of our problem-solving strategy. First, identify the forces that are acting on your object, and based on that, draw your free body diagram. Once you have your free body diagram drawn, you can write out your Newton's second law in component form, generally like you see above. Then, you get to the part where you actually try to solve the problem. Now, even though there are just like an infinite number of problems you could have with this material, there's really only two routes that can be taken, like two paths. And so this third step is very helpful, I think, to have as a reference whenever you're trying to work out a problem like this. For example, if the problem is asking you to determine a position or a velocity, you're going to have to first find the acceleration using kinematics. In other words, kinematics means the old material, so that could be one of those three big equations we used in the past, or the definition of acceleration. Excuse me, I said that backwards. I'm sorry. You're going to solve for A first using the equations you have given above. Then you're going to use kinematics to determine the position or velocity. Excuse me. I'm sorry about that. So you're going to use kinematics to solve for a position or velocity. That means one of those big three equations that we talked about in the past. Or if you're asked to solve for a force, then you have to go back into the past a little bit and use kinematics to get your acceleration and then solve for the force. So either way, what's important to note is that you need to know the acceleration in these problems. You're going to be solving for acceleration before you get your answer, regardless of the path that you take. So that's very important to keep in mind. Now, the problem might give you the acceleration. In that event, then you're fine. You can just go right into solving. But that's rare. So with this in mind, let's go ahead and work out a problem. Example 1. If you were watching my last lecture, this is actually the exact same example as what we saw in the previous lecture. So I'm going to kind of go quickly through the free body diagram and Newton's laws because we already did this in the last lecture. So I encourage you, if you're just jumping in now, to go back one lecture and watch that one before we work on this problem. This one says, with the same words as before, a car with a mass of 1,500 kilograms is towed at a steady speed by a rope held at 20 degrees from the horizontal. A friction force of 320 newtons opposes the car's motion. What is the tension in the rope? Here's the key. If the car goes from rest to 12 meters per second in 10 seconds. In the last problem we did like this, it said that the car was being pulled at a steady speed, but now it is not. So let's see how this affects our problem. We want to draw a free body diagram again, but it's the same as the one we saw in that past example. So please understand that we are just going to use the same free body diagram as before. Acting on the car is a weight pulling downward, a normal force from the surface pushing back upward, perpendicular to the surface. There is a kinetic friction force resisting the car's motion, and there's a tension force in the direction of the rope that is pulling on the vehicle. Now, we can use our trig, again, to recall that there's going to be an x and a y component of this tension. So we can say the x component, this is the adjacent side, is going to be t cosine theta. And the y component, or this vertical piece, is the opposite side of the angle. So the y component is going to use sine. In other words, t sine theta. So we did this already. I'm just going through it again. That was step 1 of this new problem-solving strategy. Step 2 says to write down Newton's second law in component form. So that is the sum of fx and the sum of fy equations. So again, we did this already. So in the x direction, in the positive direction, we have the x component of the tension, or t cosine theta. And in the negative direction, we have the friction pointing to the left. In the y direction, we have 3 forces: the vertical component of the tension, or t sine theta, plus the normal force also pointing upward, minus the weight pointing downward. Now, this is where students can get confused. Think about what's happening in this problem. In the x direction, horizontally, we're told that the car goes from rest to 12 meters per second. It is accelerating. So we can't set this equal to 0 like we did in the previous example. We need to set this equal to the full ma. F equals ma. However, in the y direction, think to yourself, is the car accelerating up off the ground or down into the ground? Well, no. There's no acceleration vertically. So in this case, the acceleration is 0, and so we can just put a 0 here. Okay, so it is accelerating along the ground, but vertically, it's not being accelerated up off the ground or down into the ground, so this one is set equal to 0. These are our Newton's second law in component form equations. Now we have to think about solving. Let's think about our problem-solving strategy. I'm going to hop back for a second. So in this case, we are told to solve for the tension in the rope. In other words, we are asked to figure out a force. So we should use kinematics to get the acceleration. So let's do that. We want to solve for the tension. We can't use the second equation here because we don't know what the normal force is, which means we have to use the x equation to solve. So if that is true, and we want to solve for tension T, we need to know everything else in the equation. Theta, which we do know, the friction force, which we do know, the mass, which we know, but we don't know the acceleration. So this is where the acceleration has to be found from kinematics, in other words, past material. Thankfully, it's not that complicated. We want to solve for the acceleration. Well, the acceleration is by definition your change in velocity over change in time. So let's just solve for acceleration this way. We're going from rest to 12 meters per second. So we have 12 meters per second minus 0 meters per second, final minus initial, over the time, which we're told in the problem is 10 seconds. So we have 12 divided by 10, or 1.2 meters per second squared. Okay, so even though we have that problem-solving strategy telling us to solve for the acceleration, we kind of reasoned that we'd have to anyways, because to solve for t, we need to know a. So using the definition of acceleration, we were able to determine the acceleration as 1.2 meters per second squared. Now we can actually solve. So we are able to now solve. So let's bring in our x equation and solve. We have t cosine theta minus the friction equal to max. Solving for tension would imply that we have to add friction to the other side and then divide by cosine theta. So we'll have the following. Tension is equal to max plus the friction, and then all of that divided by cosine of theta. Okay, so that's just a little algebra there. Add friction, then divide by cosine. At this point, we have what we need, so we can plug everything in and solve. This might take up a bit of space, but the mass is 1,500 kilograms. The acceleration we just solved for is 1.2 meters per second squared. Then we add the friction, which was given in the problem, as 320 newtons. All of that gets divided by cosine of the angle, which was 20 degrees. Hopefully, we've set everything up right to this point. We can now plug these numbers in. Hopefully, we do it right in the calculator as well. And this should give us a value of roughly 2,300 newtons of tension in the rope. Now, this is considerably more tension than in the problem we did in the last lecture. Same problem, a car being towed, but it was being towed at a constant steady speed. That tension that we solved for was only 340 newtons, but now it's 2,300, which makes sense if you think about it. Being much larger, we are now pulling on the rope to accelerate the car. So we're basically, in a way, pulling with a larger force. So we're going to see a bigger tension in the rope as a result. All right. Well, this brings us to the last example. In this example, and this is a good question, I like this one, it says the following. A golfer putts a 46-gram ball with a speed of 3 meters per second. Friction exerts a 0.02 Newton retarding force on the ball, slowing it down. This question asks, and it's a good question, will her putt reach the hole that's 10 meters away? All right. Well, we start this problem like any other. Let's draw a free body diagram. So we're going to start there by writing down our axes, or drawing our axes, x and y, and representing our object as a dot at the center. We now want to draw in the different forces that we have as vectors. So think about what forces are acting on the golf ball. Well, like everything else on Earth, it has a weight that points downward. The ball is on a surface, and so it should be experiencing a normal force from that surface. This should be drawn the same size or length as the weight. I want to draw that so it's upward. Well, just imagine this is pointing straight up. I just didn't do that well. We have a normal force pointing straight up from the surface. And as it states, there's also a friction force resisting the motion. So that's going to point in the opposite direction of its motion, our kinetic friction. This is our free body diagram. So, based on this free body diagram, we move on to step number 2 of our problem-solving strategy, which just says to write down the Newton's laws based on this. And I forget, I have I have the free body diagram here. So let me just erase all of this. It looks a lot prettier on that diagram than what I drew, so let's go with that one. So we have this free body diagram now. So let's go ahead and work out our Newton's laws. Sum up the forces in the x and y directions. I meant to write an x there. In the x direction, we have only one force, which is interesting. The only force in the x direction is friction, and that's pointing to the left. So that's going to be a negative friction value. But there is an acceleration here, right? The object is slowing down. So we do set this equal to ma. There is an acceleration. We can't set it equal to 0. Let's do the same thing for the y direction. Vertically, we have two forces. We have the positive normal force because it's pointing upward, and a negative weight force because it's pointing downward. But the ball is not accelerating up or down, and so this is just equal to 0. Okay, that was step 2. At this point, we go to step 3, trying to solve the problem. Well, let's go back to our problem-solving strategy for a second. In this case, we are asked to determine how far away the ball goes, right? Does it reach the hole? So in this case, we are looking for a position. So if that's the case, we need to first solve for A, then use this kinematics to determine the position and velocity. So we need to first solve for the acceleration. And you would know to do this anyways, because if you recall the 3 equations that we used in the past, those 3 big kinematics equations, all of them require you to know the acceleration. So there's no way for you to figure out the position of the ball without the acceleration being known. So we have to find it first. So let's do this. We need to first find the acceleration from one of these equations. So the acceleration only shows up in one place, from the x equation, so let's solve for it here. Based on that equation, the acceleration is going to equal the negative kinetic friction divided by the mass. Right? All I did was divide mass to the other side. We know both of these values, keeping in mind that mass should be in kilograms. So we have negative 0.020 newtons, that's the friction force that was given in the problem, divided by the mass, which is 46 grams, in other words, 0.046 kilograms. This comes out to an acceleration of negative 0.435 meters per second squared. Okay. We now know the acceleration, which means we can now plug that into one of those 3 big kinematic equations of the past. Hopefully you recall what those equations are. I suppose I could just write them here really quickly, just for reference. So we had 3 equations, 1, 2, and 3. The first said Vx final equals Vx initial plus Ax delta t. The second equation said x final equals x initial plus Vx initial delta t plus 1/2 Ax delta t squared. The third equation was Vx final squared equals Vx initial squared plus 2 Ax delta x. So it took me a minute to write that, but it is helpful to see them all in one place here. So our goal is to figure out which equation we need to solve in order to get a position, right? How far away the putt makes it. In this case, we have one really important piece of information missing, and that is the time. We don't know how long it takes for the ball to move along the ground. And so as a result, we have to choose the one equation out of the three that does not have time in it. And that is our third equation, the time-independent equation. Notice that there's no delta t in there, and so we are able to use that equation to solve for the position. So let's start with that equation. I'm going to write it again, even though it's right over there. We have Vx final squared equals Vx initial squared plus 2ax delta x. So we're looking for how far the ball goes. In other words, we're looking for delta x, or you can think of it as x final. So let's rearrange this for delta x. Well, subtract Vx initial over. So we're going to have Vx final squared minus Vx initial squared. And then divide all of that by 2a. So we see the following equation. This is what we need to use to solve. So let's go ahead and do this. We do know all of these values, so we can indeed solve. Vx final, well, think about what's happening here. The ball is coming to a stop, right? We want to see how far the ball goes. Well, the ball is going to go as far as it can until it stops. So its final velocity is 0 meters per second. The initial velocity is given to us. It says that she hits the ball at 3.0 meters per second. All of this is divided by 2 times the acceleration that we just solved for, negative 0.435 meters per second squared. So just plug this into your calculator. Notice that the negatives are going to cancel each other out and give us a total distance traveled for the ball of 10.3 meters. Well, the hole is 10 meters away. The ball can travel 10.3 meters. So our answer is yes. The putt can make it to the hole based on the information given to us. Okay. So there's a little bit more work involved with these dynamics problems compared to the equilibrium ones that we saw in our previous lecture. This last step here, where you have to use some kinematics or old material, can really confuse people. So please, maybe rewatch this or practice this as much as possible so that you have it down. Because unfortunately, this still gets expanded on more. In future lectures, we're going to take a look at how each individual force, like friction or weight, has its own equation associated with it. So we still build on this a little bit more. But overall, I'd say we're just about at or nearing the peak in terms of difficulty. But again, in order to understand future work, you need to understand this. So review this material as much as necessary. Let's conclude this lecture with just one multiple choice question. This question says a ring is pulled on by 3 forces as shown. The ring is not moving. So how big is the force F? Okay. Well, to figure this out, we have to understand how forces work now. Realize that you have 2 forces here, one on each side, that form a triangle. It says that the object is not moving. If the object is not moving, our forces should be balanced, which means the force F pointing downward has to be equal to the 2 forces pointing upward. So we need to figure out how big each force is that's pointing upward. Well, the vertical component of this, the upward part of it, is the opposite side of the triangle. So that would be, if you write it over here, this would be 10 sine theta, right? This is the opposite side, so we use the sine function, so it's 10 sine theta. Well, we have it over here too. We have a vertical piece, which is the opposite side of the angle, so this is also 10 sine theta. So again, for our forces to be balanced such that the ring does not move, these two forces have to combine to equal the force F, so that it's balanced. So we have 2 times 10 sine of theta, which gives us 20 sine theta. The answer is E. Okay. Well, hopefully, after numerous examples, this is starting to click a little bit, but I know it's not easy. So hopefully, though, we're building on it. We're going to keep building on it. If we don't get it entirely now, let's keep building and see if we can down the road. Until the next lecture, thanks for watching and have a great day.